Hello everyone, welcome to the Math Club talk. Today's talk is the continuation of yesterday's talk on the topic conjugacy classes and irreducible representations of a group. The speaker is Shahbaz Ahmed Khan. He is a B.Math second year student whose interests lie in group theory, representation theory, and combinatorics. If anyone has any questions during the talk, you can type it in the chat. I will convey it to the speaker. So yeah, over to you, Shahbaz.
Thank you, Harshil. So I'll be developing on what we discussed yesterday, and today we'll reach the end result. That was the goal of these talks, to prove a restriction on the number of conjugacy classes using ideas from representation theory. Okay. So as yesterday, my notation remains same. All vector spaces will be finite dimensional and over the complex numbers. All groups are assumed to be finite. I also reserve the symbols phi, psi, and rho to denote representations, and the letters v and w to denote vector spaces. Okay. So from yesterday, we recall that a representation of a group G is a homomorphism phi from G to GLV for some vector space V. Representation is said to be irreducible if the only G invariant subspaces of V are 0 and the entire vector space. And I defined the character of a representation phi to be a function from G to C, such that chi phi of G is the trace of the matrix phi G. And we also stated that if phi1 to phi s denote a complete set of inequivalent, irreducible, and unitary representations of G, and we said di to be the degree of phi I, okay, same type as yesterday, and chi I to be chi phi I, then the formula order of G is equal to summation of the degrees squared holds. Okay. So given a representation phi from G to GLDC, I define a new representation called the conjugate representation of phi by simply setting the conjugate representation using this equality. So it maps to the conjugate matrix that I would have otherwise got without taking the conjugate. And in general, for a function f from G to C, I define the conjugate to be the conjugate of the value. I will be using this in particular, so note that the characters are such functions. And we'll see how the characters behave under conjugate representations. Similarly, given a matrix, I define its conjugate to be the matrix with entries being conjugates of all the original entries. And it is straightforward to notice that AB conjugate is A conjugate times B conjugate. And if A is an invertible matrix, then so is A conjugate. And this equality gives us the inverse. Okay. So yesterday we had the trivial representation, this one. The conjugate, obviously the conjugate of 1 is always going to be 1. So this representation is equal to its conjugate. We also saw a representation from Z mod to Z to C star defined by k going to -1 to the power k. This is again trivially equal to its conjugate representation since this thing is entirely real. If I define a representation from Z mod 4Z to C star by k going to iota to the power k, then the conjugate representation is not equal. So we will be interested in the situation where there is some sort of equality between the representation and the conjugate representations. Okay. Now the character of a representation. So remember that for phi, the character of phi is this function. Now, in general, for any matrix, it's obvious that the trace of A conjugate will be the conjugate of the trace of A, since by definition, the elements are simply conjugates of the original entries, and the trace can be split over summations. And so in particular, if I look at the character function, that is the trace of phi G conjugate, then that's simply the trace of, or rather the conjugate of the trace of phi G, which is exactly the conjugate of the character function of phi. Okay. And again, Another thing that's preserved when taking conjugate representations is irreducibility. So if phi is an irreducible representation, then so is the conjugate. This is useful because we are often interested in knowing all the characters, all the irreducible characters of a group. So if you find an irreducible character, then using this proposition along with this corollary, you can come up with one more irreducible representation, unless of course they turn out to be equal. So the proof is again straightforward. If chi is the character of phi, then the conjugate of chi is the character of the conjugate of phi. And then you can simply calculate the scalar product of chi bar with itself, and that turns out to be 1, which we saw in yesterday's talk implies that the representation is irreducible. Okay. I'll need two more basic facts. So in a group G, say the elements G and H are conjugate. Then I say that G inverse and H inverse are also conjugate. This is again straightforward. So if G and H are conjugate, then there is some X in the group for which this holds. And then if I invert this, I get G inverse is XH X inverse inverse, which is X inverse H inverse X. I hope I've written that correctly, but yeah. And this implies that G inverse and H inverse are conjugate. So yeah, so inverses are also conjugates when two elements are conjugates. And if chi is the character of a group G, then the character of the inverse of that element is simply the conjugate of the character on that element. To prove this, to easily prove this, I can, without any loss of generality, assume that the representation to which chi is associated is unitary. This doesn't lose me any generality because we saw yesterday that every representation is equivalent to some unitary representation, and the characters are preserved under equivalence. So if I take chi to be associated to some unitary representation, then chi G inverse is given by the trace of phi G inverse, which then, since this matrix is unitary, is equal to this matrix. So the trace is also equal to the trace of that matrix. And taking the transpose, so this T here indicates transpose, that doesn't affect the trace since the diagonal elements remain where they are. And then you get the equality. Okay. Real characters and real conjugacy classes. Okay. So let C be a conjugacy class of a group. By C inverse, I will denote the set G inverse such that G belongs to C. Clearly, C inverse is also a conjugacy class. This is because GH conjugate is the same as saying G inverse H inverse conjugate. And note that the character of C inverse is, or rather the image of chi on C inverse is the same as the conjugate of the image. By conjugate of the image, I just mean this set. And this is true because we just saw that chi G inverse is chi G conjugate. Okay, I define a character to be real if it's equal to its conjugate. So this is obvious. This just means that chi G is chi G conjugate for all G. I've written it in shorthand. Or in other words, chi G belongs to R for all G. I define a conjugacy class to be real if C is equal to C inverse, which isn't really how we usually go about looking at real things. We usually want them to be equal to the conjugate, but because of this equality that we saw, this makes sense. Okay, so let C be a real conjugacy class and chi be a character of G, then chi C is conjugate of chi C. This is true because chi C is chi C inverse conjugate, and C is a real conjugacy class, so this is equal to chi C inverse. Right. Let's see the conjugacy class and chi be a character G, then chi C is chi C conjugate. Oh yeah, and then this is chi C from the notation or the previous note. Okay. Now, yesterday we saw the standard representation of Sn as well. I'll define it once more. So the representation phi of the symmetric group on n symbols to GL and C is defined on the standard basis by phi sigma of EI is E sigma I. So the standard basis is all these things and so on. And we can obtain the matrix for phi sigma by permuting the rows of the identity matrix according to sigma. Now I give a lemma that will make calculation easier later in the talk. And okay, so let phi be the standard representation of Sn and consider any n cross n matrix over C. Then for any permutation in Sn sigma, the matrix phi sigma A is obtained from A by permuting the rows of A according to sigma. And A sigma phi is obtained from A by permuting the columns of A according to sigma inverse. So in other words, I can multiply on the left side and the right side quite easily. Okay. I proved this, and it's not a very complicated proof. You just need to calculate the entries explicitly. So we have this equality which holds. Oh, sorry. And if we now observe that this also holds. So the reason this holds is that the matrix of chi sigma has only a single one in each row and a single one in each column. And we start with the identity. The only way that you get the entry 1 at any given point is if this happens. So the only way to get a 1 at this entry is if this happens. Otherwise, you get a 0 simply because of the way it's constructed. And then you can explicitly calculate it out and you get the result. This is straightforward and not very elegant computation. Okay. I also defined direct sums today. I won't be needing this, but I want to define the character table, and it's kind of pointless to define that without direct sums. So if phi and rho are two representations over two different vector spaces possibly, then we define their direct sum to be a representation into this vector space given by this equation. And it's easy to write their matrix if you have if v1 is some c to the power m and v2 is cn, then the matrix is simply given by this neat block form. And obviously you can then observe that the characters are added up since the trace will obviously be added up. So this makes it useful to know all the characters and write them down, because then you can come up with any representation, any character. If you know all the irreducible characters, you can just add them up according to how it decomposes. Of course, that's not something I've discussed, but makes intuitive sense. Okay, character tables. This was the quick to get through part. Now we get into the nitty gritty. So let G be a finite group with irreducible characters chi1 to chi-s and conjugacy classes C1 to Cs. Obviously, these are equal in quantity. We saw this yesterday. Then the character table of G is the S cross S matrix X, whose ijth entry is given by chi i's value on the conjugacy class Cj. So remember that so this equality is well defined. It's not like I can get two different values depending on what element I take from Cj. Okay. In other words, it is the matrix with rows indexed by the characters of G and columns indexed by the conjugacy classes of G. And the ij entry is the value of the ith character on the jth conjugacy class. Remember that characters are class functions, so the value on a given conjugacy is constant. Okay. Now I'll draw a few character tables just so we get a feel for this. I start with S3. So obviously S3 admits the trivial character, which is also irreducible, given by chi1 sigma is equal to 1 for all. Okay, I should first come up with all the conjugacy classes of S3, which is not again very difficult. So S3 I denote by ID 1 2 1 3 2 3 1 2 3 and 1 3 2. Then the conjugacy classes are, this is obviously just identity. For 1 2 it will be 1 2 1 3. So in the previous talk, we had seen an irreducible representation row defined on the generators by this thing, these two matrices. And we can find the character of this now, which is just a case of adding two numbers together. And if I let that be chi2, then from this I observe that chi2 on this conjugacy class is going to be 0, and on this conjugacy class it's going to be -1. So I get 1, 0, and oh, okay, this will be 2 here because I have a degree 2 representation, and -1. Now I magically come up, okay, so now I want to find one more irreducible representation or a character. And now I know that chi3 will have degree 1. And that's because the order of S3 is 6. And I already have a degree 1 representation and a degree 2 representation. So d square for the last representation is 1. That is, it is 1. So the last representation is of degree 1. And I magically come up with the example or a representation which works, which is given by this. Now, again, now we can simply write the character table using our knowledge of this representation, and that gives me 1, -1, and 1. Yeah, it should be correct, I hope. If I look at this matrix now, this turns out to be invertible. And this is not something that happens in particular with S3 or even with just representations of symmetric groups. This happens every time. And now that we know what a character table is, if I go back to something I mentioned in the first talk, the second orthogonality relations, it's immediately obvious that this relation tells me that the columns of my character table are going to be orthogonal. or in other words, the character table will be an invertible matrix. So I mentioned this here as well. Character tables are invertible. I'll draw a few more examples, though I won't explain those, but just for entertainment, I suppose. For Z mod 4Z, the character table looks something like this. So conjugacy classes can be represented like so. And there are 4 characters. Obviously, you have this and this. You have a -1, 1, -1, I, -1, -I. And using this one, I can come up with the last one, which would be the conjugate. That's 1. And for abelian groups, it's actually easier to do something with them. For Z mod 2Z, I tell you that the character table is something of this form. 1, 1, 1, -1. But then I can immediately then also tell you, using a result I'm not mentioning, that the character table of this group will then be something of this form. 1, 0, and 1, 1, omitting the square brackets to save space. And my characters are these. Then the character table is something like this. In general, the result is something like you have 2 abelian groups, and if you have all their irreducible representations, so say for G1 and G2, you have chi1 to chi-m and some phi1 to phi-n are irreducible representations, then you can take their products, so their Cartesian products, G1 cross G2, and you can find all the irreducible representations quite easily. I mentioned one result without proof today because developing this proof would take some tedious work. And that is that if phi is an irreducible representation of G of some degree D, then the degree divides the order of the group. In order to prove this, we need to use the first orthogonality relations and the fact that if chi is the character, then chi G is always an algebraic integer. And so is this h chi G over D term, where h is the size of the conjugacy class. This will take some, I would have to have developed some amount of knowledge about algebraic integers to prove this, so I choose not to. Maybe if there's time left in the end, we can come back to this. Okay, now we move on to the 2 main results and a proposition in between them. Equals number of real conjugacy classes of G, that is, conjugacy classes will satisfy this. Okay, to prove this, let S be the number of conjugacy classes of G. Then you have S inequivalent irreducible characters of G and S conjugacy classes of G. I denote them by chi1 to chi-s and c1 to cs. I define, or rather I fix some alpha and beta in SS. So SS here is the symmetric group. On S symbols. so capital S, small s. Define alpha comma beta to be some fixed permutations in SS by these two equations that I magically come up with. But you notice that these are always going to work, and that is because chi I is irreducible. So let's look at this one. Chi I is irreducible, which implies its conjugate is irreducible. But since chi1 to chi-s are all the irreducible characters, this implies that chi-I conjugate must also be in this set. That is, it is chi alpha I for some alpha. And similarly, I define C, or I define beta to be such that Ci inverse is C beta I, which again holds due to a similar reasoning. Now, if chi I is a real character, then chi I is equal to chi I conjugate, or chi I is equal to chi alpha I, which implies that I is equal to alpha I. So chi I is a real character if and only if I and alpha I are equal. And the number of I for which this happens, so fix of alpha is the set I such that I is equal to alpha I. So all the elements that it leaves untouched, which it leaves in the original places, then chi I is a real character if and only if I and alpha I are equal. And we can say that fix of alpha is the number of real irreducible characters of G. Similarly, the fix of beta will be the number of real conjugacy classes of G. Fix of beta is again just all I such that I is equal to beta I. Okay. So now I want to find something that tells me fix of alpha and fix of beta are equal. So I look at the standard representation of SS. And using the lemma that we proved previously, I can now easily multiply matrices on the left and right side. So let X be the character table of G. And we know that X is invertible. Then X is, of course, an S cross S matrix. And by our previous lemma, phi alpha X can be obtained by swapping the rows of X corresponding to Xi. And X alpha I for each I. This means that this holds. Similarly, for X phi beta, you get that something of this form holds. So what this implies then is that X conjugate is X phi beta. So you have this, that these three matrices are equal. And this then implies that phi alpha is X inverse, or rather X phi beta, X inverse. And now the proof is more or less done. So the trace is equal. The trace is equal since trace of X phi beta X inverse is the same as the trace of X inverse phi beta. X inverse give you identity, and d times phi beta is just phi beta, and therefore the proof is complete. Now, before moving to the punchline of these two talks, the final result, I need one more proposition. So let G be a group, then mod G is odd if and only if G does not have any non-trivial, real irreducible characters. Okay, so by the previous theorem, I only need to show that mod G is odd if and only if the trivial subgroup, or rather the conjugacy class generated by identity, is the only real conjugacy class of G. So suppose mod G is even, then there exists G belonging to G such that G and G inverse are equal. The conjugacy class of G is then clearly real. Therefore, if mod G is not odd, then mod G has non-trivial real conjugacy classes. Conversely, suppose that G contains a non-trivial real conjugacy class C, and let G belong to C. From group theory, we know that if we consider the normalizer of G, then this equality works. And we try to show that our assumption implies that G has an element of even order, therefore implying that mod G is even and completing the proof. So suppose HG H inverse is equal to G inverse. Now, why can I do this? I can do this because I am assuming that G contains a non-trivial real conjugacy class and G is in that. So you take that and you square it, then you get something of this form. So HG H squared G is HG H inverse which is HG inverse H inverse. So that is this equality, which is clearly the same as HG H inverse, which is G inverse inverse, which is G. So that gives you these equalities. And therefore, H square is in the normalizer of G. If H itself is of even order, then we are obviously done. Otherwise, if H has odd order, then suppose the order is some 2k minus 1, then H to the power 2k minus 1 is identity, which implies H to the power 2k is again H. So H lies in the subgroup generated by H square, and thus H belongs to the normalizer, since the normalizer is also a subgroup and it contains H square. So it must contain the subgroup generated by H square. Then G and HG H inverse are equal, and that's equal to G inverse. So G square is identity, which gives you an order 2 element, implying that the order of the group must be even. Therefore, the proof is complete. And we seem to be running fairly ahead of schedule. So are there any questions so far? Feel free to unmute if you'd like to. Okay. So now I come to the main result of this talk, which is a result given by Burnside. And after this, I'll mention some more results that I maybe will see some proofs of. But this will be the main result that I will be proving. So let G be a group of odd order, and let S be the number of conjugacy classes of G. Then this congruence holds. So I have a fairly strong restriction on the number of conjugacy classes for groups of odd order. Okay. So since mod G is odd, the only real irreducible character of G is the trivial character chi1. This follows from this proposition that we just saw. So mod G is odd if and only if G does not have any non-trivial real irreducible characters. So the rest of the irreducible characters appear in conjugate pairs. Now, why do I know this? Because since none of them are real, the conjugate character is never going to be equal to the original character. So I can come up with 2k characters quite easily, or rather here 2k being s minus 1, since I already assume that the number of conjugacy classes is s. And also because we saw that the order of the group is the summation over the degree squared. So then mod G is degree chi1 squared plus degree chi2 squared plus degree chi2 conjugate squared and so on. And the degree of conjugates is equal, obviously. This also holds. And this is about all the build-up of rep theory that was needed for this proof, since now we just do some manipulation and the result follows. So this is the result I mentioned without proof, that the degree of irreducible characters divides the order of the group. So since dj divides mod g for all j, it has to be odd for all values of j. So you let dj be some 2mj plus 1 for some non-negative integer mj. Then mod g, which was equal to, so I'm using this equality there, and I expand it. So mod g is 1 plus the summation over 2 times 2mj plus 1 whole squared. I have the 1 here, that's chi1 squared. So that's the degree 1 representation. I expand this bracket, I get 1 plus summation over 8mj squared plus 8mj plus 2. I can then get this 2, which doesn't rely on mj, out of the summation, which gives me this 2k. And I have an 8 here. Now, since I know what I'm trying to prove, I'd like this to be even, which it clearly is, since if mj is odd, then mj plus 1 is even, and if mj plus 1 is odd, then mj has to be even. So every single summand is even. Therefore, the entire summation is even. So when I go mod 16, this thing becomes 0. And therefore, mod g is congruent to 1 plus 2k mod 16. Or in other words, mod g is congruent to the number of conjugacy classes mod 16, which is the same as saying. And that's the main result. So I wanted to mention some more results, and it's good since we seem to have come around 10-15 minutes below time. So I'll mention some more results that have representation theoretic proofs. Maybe I'll discuss some of the proofs now that we have time. And I begin with 2 more results credited to Burnside. One of them is called the lemma of Burnside. I'm sure there's plenty more that are called lemmas by Burnside. So if sigma is a group action from G to Sx and m is the number of orbits of G on X, then m is 1 over mod G and summation over fixed G. A famous result of Burnside is that let G be a group of order p to the power a and q to the power p, with pq being primes, then G is not simple unless it is cyclic of prime order. If my memory serves me right, then this result is famous for not having had a purely group theoretic proof for a long while, and the only proof that was previously known was the one involving representation theory. Okay, so maybe I can prove Burnside's lemma. It's a straightforward proof, I believe. I add a page. I am sure I'll be using something I haven't talked about in the talks, but it should be interesting to see it nonetheless. So to prove Burnside's lemma, that is, let sigma from be a group action. Let m be the number of orbits. Then m is equal to 1 over mod G. So to prove this, you need the permutation representation, rather the idea. But without really going too much detail, I'll just write down the proof. Maybe some of the audience knows representation theory, so it's clear to them. And so yeah, so let chi1 be the trivial character. Then you know that this holds. So I'm obviously skipping over a lot of details. So the sigma tilde here denotes the permutation representation associated to the group action sigma, whatever that means. and I already know, so this can be proven without having to involve this lemma, that this is the same thing as this. Yeah, so obviously not a very detailed proof, but it at least tells us that it can be done. Obviously, I won't be proving Burnside's theorem. That would be a two-talk series in its own. But a few more. Let P be a prime and let G be a group of order P square. Then G is an abelian group. This is not very difficult to prove. So I do prove this one. So yeah, let P be a prime. And G is a group of order P square. This implies G is abelian. So the way you prove this is that you assume that let d1 to ds be the degrees of the irreducible characters of G, and mod G is P square. So I mentioned during this talk that then di will divide P square for all I. So di can only be one of these three values for each and every I. Now, of course, since the trivial representation is always there, you can, without loss of generality, let d1 be 1. So corresponding to the trivial character, trivial representation. And now since mod G summation over di squared, which is now 1 plus summation over di squared, you see that p square minus 1 is supposed to be this thing. And this tells you that it is 1 for all I, which tells you that G is abelian. Another one is that let PQ be primes with P less than Q, and okay, this should be Q not congruent to 1 mod P, I believe. I'll check if you give me a second. Okay, this should be correct, but since I'm doubtful, let's not bother with the proof. Another famous result that can be proved using representation theory, I chose not to mention it earlier, is called Wedderburn's theorem. And whatever this means. So I don't think I have much more left to say for today. That should be all. Are there any questions? If not, then I believe this should be the end of this talk.
If anyone has any comments or questions, you can just unmute yourself and speak.
What is the idea of the proof of the last thing, that the Wedderburn's theorem?
To prove Wedderburn's theorem, you need to you need Fourier transforms, discrete Fourier transforms, and that helps you prove this. Maybe I can in the future give a talk on this as well, but the book that I've studied from dedicates an entire chapter to just this proof. So obviously it won't be easy for me to mention immediately. In brief, so you need convolution on the Fourier transform and how it works on finite groups, and that leads to the proof. So first you show that it is a vector space isomorphism, and then you do some manipulations to reach the fact that it is indeed a ring isomorphism as well.
Okay. And given any group, is there any process for how can we determine the degrees of the irreducible representations?
Not exactly. It's more of an art than a science. So obviously you have some constraints, like there's always going to be one representation of degree one. You're always going to find conjugate representations, and some of them won't be equal, but and that they divide the order of the group. But it's more of a trial and error thing. There's no precise way to just say that given this group, these are all the
Yes, so
irreducible
this
degrees.
isomorphism is not easy to construct then for any group, right?
Yeah, but once you have that, it becomes when the group is not something very nice, then it becomes slightly non-trivial to even do that.
Okay, okay.
Any other questions?
I guess that's it. So yeah, thank you for the talk, Shahbaz. We will meet tomorrow. We will meet next Saturday and Sunday, most probably at 12 only. The topic and the speaker will be announced midweek. So yeah, thank you everyone for attending. Bye.